Hello, and welcome to this virtual lecture course on the quantum theory of condensed matter physics. I'm Dr. Andrew Mitchell, and in this lecture I want to talk about topological quantum matter. In some of the previous lectures of this course, we've been discussing first how to formulate and then how to solve quantum many-body systems. In this lecture, I want to talk about a particular class of those systems, so-called topological systems. These are systems that have some kind of quantum information stored non-locally in the system, and the excitations or quasiparticles in this system are topologically protected, meaning that they're robust to decoherence from local perturbations. And it's precisely because of this fact that these systems have been discussed a lot in the academic literature recently for their possible use in topological quantum computation. There, we want to be able to protect our quantum information from local perturbations and decoherence, and this is one possible route to doing that. So although we'll only discuss toy models and simple systems in this particular lecture, we'll see that there's great potential for this kind of physics. The two models we'll be discussing are the so-called Su-Schrieffer-Heeger model, or SSH model, which describes a 1D chain where we have exponentially localized zero-energy states living at the ends of the chain, which are robust to perturbations. We'll also talk about the Kitaev chain, which is a variant on this system with additional superconducting terms. We'll see how this gives rise to Majorana quasiparticles. These Majorana states live at zero energy and are their own antiparticle. Of course, no fundamental particles for this property exist in nature, but these are emergent quasiparticles living in these condensed matter systems. So we'll study both of these things. We'll talk about the transfer matrix method, we'll talk about the spectral functions, we'll talk about these protected zero energy states in these systems. So let's get down to work.
So in this lecture we'll be discussing topological quantum matter. This is actually rather a vast and rich topic. It's also rather a recent subject. This lecture is intended to be more of an introduction to give you a taster for some of the interesting concepts. And we'll do that using two paradigmatic models of topological quantum matter. These are so-called toy models. They're not supposed to directly correspond to a physical system, but they highlight in the simplest possible way some of the important features. Of course, there are models of realistic systems which are topological in nature, and we'll touch on those just at the end. But most of the lecture will be spent studying these two simple models. And those models are the Su-Schrieffer-Heeger model or the SSH model, and also the Kitaev chain. So there are many other kinds of models we can study, but these are probably two of the most famous ones. Alexei Kitaev, who invented this Kitaev chain model, has actually many interesting models attached to his name. This is the one-dimensional chain version. So both of these models have some things in common. They're both one-dimensional systems, and they're both insulating in the bulk. And by the bulk, what I mean is sort of deep in the middle of the 1D system, far away from the edges. However, there are also some differences. The Su-Schrieffer-Heeger model is a system which is a band insulator. It has 2 sites per unit cell, whereas the Kitaev chain has a single site in its unit cell, but it also has a superconducting pairing term in the Hamiltonian. The resulting physics has some features in common. Both models have a gapped spectrum with a localized edge state in a topological phase, which sits right at the edge of the chain and is isolated from the rest of the bulk. It's exponentially localized if you look at the wave function. But there are also some differences. In the SSH model, living at the end of the chain are regular fermionic states, whereas living at the end of the Kitaev chain are so-called Majorana bound states. They're sort of like a half a fermion, and only when you take the two ends of the chain together can you reconstruct a whole fermionic state, a qubit state. And the detailed study of these two systems and unpacking all of these interesting things that I've summarised here is the topic of this lecture. In addition to going through the analytic structure of these systems, some pen and paper calculations, I'll also show you some numerical calculations using Mathematica. And I'll put down here, finally, number 3, a whole range of other interesting systems. There's topological insulators, probably the most famous, topological superconductors, Dirac and Weil semimetals, topological spin liquids, and also extending all of this to interacting systems with interacting topological materials. So this is a vast field with many more things that we could study. So in this lecture, we will not consider all of these interesting things. I just put it there in brackets to indicate that there are many other interesting things to follow up on after this lecture. So we actually already looked at the SSH model a little bit in the previous lecture. It is a dimerized one-dimensional chain. That is to say, it's a one-dimensional chain with alternating tunneling strengths between neighbouring sites. A very long time ago, it was proposed as a model for polyacetylene, which has this structure, and you can imagine that with these alternating single and double chemical bonds, the vertices of these things are supposed to be carbon atoms, and there's hydrogen atoms that are not drawn. You can imagine that here we have some system of like alternating strong and weak bonds in 1D. Now, as it happens, polyacetylene does not have alternating strong and weak bonds. There's a sort of chemical resonance between this structure and an alternative structure in which the strong and weak bonds are the other way around. And actually, in the real system, all of the bonds are of the same kind of averaged strength. Yet, on a theoretical level, one could consider a system which does have some kind of dimerization like this, with alternating strong and weak bonds. For example, unlike polyacetylene, one could imagine some system constituting two different atoms in a two-site unit cell, where one would genuinely have different coupling strengths. One could also imagine a Piles distortion, where some of the atoms end up closer or further apart from each other, again changing the tunneling amplitudes. So as a further motivation, let me talk more about the Piles instability. So the Piles instability is a phenomenon where at half filling, a one-dimensional chain will spontaneously distort its structure to open up a gap between the valence and conduction bands, which lowers the total energy. So this dimerization is energetically favoured at half filling. The ground state energy of the dimerized chain is lower than the homogeneous chain, since at half filling the filled valence band is moved down and lower in energy by the gap opening. So imagine a uniform or homogeneous chain like this, which is meant to be a real space depiction. So the length of the bonds between these different orbitals is supposed to be the same, and if they're equivalent orbitals, then we can imagine that the tunneling amplitude between the different orbitals, parameterized by t, let's say, is the same on all sites, or between all sites, let's say. The density of states plotted as a function of energy then has the usual single band kind of form, like this, and if we consider half filling, we imagine just filling up all of these single particle states up until the Fermi energy, which I've drawn here at 0. And that's the lowest energy state, so that's the 0 temperature state, with all of the single particle states below the Fermi level being filled. The Piles distortion, or instability, is something where the atoms distort their positions and dimerize in this fashion, so some of them are closer together and some of them are further apart. So then we end up with alternating strong bonds, drawn in blue, and weak bonds, drawn in red. And this is a spontaneous symmetry breaking. And it does that to open a gap in the single particle spectrum. So here I have again drawn the density of states as a function of energy from the Piles distorted system. And if again look at half filling, then this lower band is completely filled, that's the valence band, and the upper band is completely empty, that's the conduction band. but because the valence band has been pushed down by the gap opening, if we're at half filling, the total energy will be reduced. So the idea is that this Peierls instability is a physical mechanism which, in a quasi-1D quantum wire situation, one can obtain an SSH type model with alternating strong and weak bonds. So in summary, the SSH model was introduced to describe polyacetylene. It doesn't really describe polyacetylene, but it does describe Peierls distorted systems and other systems, and it does have some fascinating properties which we'll now discuss. So this is actually the cartoon I would prefer to draw to describe this system, and on here I'll denote the unit cell as this two-site object. And for example, if this is unit cell n, then this neighbouring one would be the unit cell n plus 1, and this one would be unit cell n plus 2, and so on. So we can divide the one-dimensional chain up into these unit cells, and within the unit cell, I will label the left-hand atom as A, or the left-hand quantum orbital, should we say, as A, and the right-hand one as orbital B. And here I've denoted the intra-unit cell with this red bond. Let's call that T primed. It's a tunneling strength T primed, whereas the blue bond here, which goes between the unit cells, the inter-unit cell, I'm going to call T. So we have alternating T's and T primes. As I'm indicating here. Now you can already see from this cartoon that there may be differences depending on how the chain terminates. So does the chain end with an A site, or does the chain end with a B site? You could imagine having an infinite chain like this and then cutting it somewhere into two halves. In that case, one of the chains will end with an A site and one of them will end with a B site by construction. And independently of where we cut, we're guaranteed to get one of each type. And actually, it turns out, as we'll see, that these two chains behave rather differently. The way in which the chain ends actually affects the properties of the system in quite a dramatic way. These two different possibilities for the chain termination result in either a topological phase or a trivial phase for the model, and we'll discuss all of that explicitly in what follows. The first step, of course, is always to write down the Hamiltonian, and this is one we saw in the previous lecture. So this is the Hamiltonian, and you see that what I've written down here is a model for an infinite system. The unit cells are labelled by x, and I'm summing from minus infinity to plus infinity. So this is an infinite system. Which we could refer to as the bulk of the system. So we don't have any edges in this system because we just have a sum from over unit cells from minus infinity to plus infinity. The chain just keeps on going forever in both directions. So as you can see, the unit cells are labelled by x, and then within each unit cell we have two sites A and B, as in our cartoon. The T primed couples A and B within a unit cell, and T couples B to A in different unit cells, in neighbouring unit cells. And of course we have two terms for each of these, because the Hamiltonian overall has to be Hermitian. This term is the Hermitian conjugate of this term. This term is the Hermitian conjugate of this term. So when we write down both terms together, the Hamiltonian is Hermitian. I can write this Hamiltonian in a slightly more compact form, where I've introduced a vector of operators for a given unit cell labelled by x, which is simply CXA and cxb. So it's just a two-element vector. Likewise, of course, we have the c vector dagger, and here we're taking the dagger of the operators, but we're also kind of assuming that this c vector was a column matrix, so here we also take the transpose of the matrix to get a row matrix. So this is what we mean by the operators. There are 2 by 2 matrices E and T featuring in this Hamiltonian, and just by comparing these two equations, which are of course supposed to be equal to each other, just a different way of writing them, then we of course can read off that this E matrix is a 2 by 2 matrix of parameters which are simply encoding the interaction between sites in the unit cell, which of course is these off-diagonal terms in this basis of T primed. If we had an on-site potential or a chemical potential in system, that would feature on the diagonal elements of this E matrix here, but I've not included that term in Hamiltonian, so I'll just leave that set to 0. I also have this matrix T, which describes the coupling between the unit cells, and again, it's very easy to see that this must be this kind of funny matrix here. Note that this is not a symmetric matrix. The forwards and backwards tunneling terms are accounted for by the two separate terms in here involving T and of course T dagger. Given that T is a real parameter in this equation, this T dagger of course is just giving the transpose, so T dagger would be simply this matrix, which is of course in the end just the transpose. And so this is the Hamiltonian written out again, and we want to diagonalize this Hamiltonian by means of a Fourier transform, as discussed in the previous lecture. So we introduce these momentum space operators ck dagger, and again these are still vector operators, so still consist of 2 operators per unit cell. We're doing the Fourier transform of the unit cells, but not within the unit cell. N here, capital N, is the total number of sites in the system, which in the end will ascend to infinity. So you can substitute this expression into the Hamiltonian and tidy it up a bit in the way that I showed you in the previous lectures, and then we'll obtain this, which is almost in diagonal form. We still have the matrix M, which is something that depends on momentum k, and this is still a 2 by 2 matrix, which is in general not yet diagonal. So let's see what structure it has. So this is the structure in terms of the matrices E and T appearing in the original Hamiltonian. I showed you how to derive this in the previous lectures, and I suggest you have a go at that yourself to make sure that you can do that. Since we know the matrices E and T, we have the following. And this matrix has a rather interesting structure. It's completely off-diagonal. There's no diagonal entries here. And the off-diagonal entries are the complex conjugate of each other. So T primed and T are real, and the exponentials here, e to the plus ik and e to the minus ik. So the off-diagonals are complex conjugates of each other. And that suggests an interesting property, and there's a certain trick to diagonalizing this matrix that I will show you now. So instead of considering the matrix M, let's consider the matrix M squared, which is just M multiplied by M, the matrix product here, of course. And because the off-diagonal elements of the original matrix M are complex conjugates of each other, we simply get this diagonal real matrix here. So this is a diagonal matrix, and indeed both of the entries on this matrix are the same, so this can be factorized, where here I is the 2 by 2 identity matrix. And I've used the relation that cos k is equal to 1/2 of e to the ik plus e to the minus ik. So M squared is a diagonal matrix, and therefore the eigenvalues of M we can read off automatically. It's simply t squared plus t prime squared plus 2t t primed cos k, and that whole expression there is like a repeated root, if you like. There are two eigenvalues of m squared, and they're equal to each other. But of course, we're not interested in m squared, we're interested in m. So what are the eigenvalues of m? Well, if we have an eigenvalue equation, such as this one, where we have some eigenvector v and some eigenvalue e, then if I just pre-multiply both sides of the equation by the matrix M again, obviously on the left-hand side I'll get m squared v, and on the right-hand side I will get e, which is just a number, times the M matrix times v again, and by using the same eigenvalue equation I can again convert this into e squared times the eigenvector. So what we've shown here is if the vector v is an eigenvector of the matrix M, then it is also an eigenvector of the matrix M squared. Furthermore, if the eigenvalue is of matrix M is e, then e squared is an eigenvalue of the matrix M squared. So because in our particular case m squared is already in diagonal form, and we know what the eigenvalues are, that's the e squareds in this equation, then very simply, to get the eigenvalues of the matrix M, we simply have to take the square root of this. And so we just take the square root and obtain this. And of course, when we take the square root, there are possibilities for either the plus or the minus sign. And actually, of course, we have a 2 by 2 matrix here, so we have two eigenvalues. Actually, we need one of each. One eigenvalue is plus, and one eigenvalue is minus. Why is that? Because to get from matrix M to the diagonalized matrix, we do a similarity transformation, and one of the things that is similar between the diagonal matrix and the original matrix is that they have the same trace and determinant. And you can see that the trace of the original matrix, which is the sum of the diagonal components, is equal to 0. So that must mean the trace of the diagonalized matrix is equal to 0, and the trace of the diagonalized matrix is of course the sum of the eigenvalues. So the sum of these eigenvalues must be equal to 0, and if they're either plus or minus the square root, we know that we need to have one of each. So the two eigenvalues I'll denote lambda plus or minus, and they're just respectively plus or minus this square root. So because we have a two-site unit cell for this problem, we have 2 by 2 matrices, and therefore, in the end, we have two eigenvalues of the matrix M. That corresponds to two bands of this system. And furthermore, what we see from the structure here is that because they're plus or minus the square root of something, generically there will be a gap that separates the two bands. So what is the size of that gap? Let's call the gap delta. That delta is equal to the minimum value of lambda plus minus lambda minus. So what is the minimum value of this thing? Well, the minimum value of this object inside the square root obviously happens when k is equal to pi, because then cos k will be equal to minus 1, and that's the smallest value that cos k can take. So the argument of the square root will be the smallest that it can be. And in that case, of course, we can simplify things a little bit and write that delta is equal to twice t minus t primed. And actually, you can see that the system is gapped whether t is greater than t primed or t is less than t primed. So the way I've written it here, this delta could either be positive or negative. If we're actually interested in the magnitude of the gap, let me write this, instead of with regular brackets, let me write it with modulus signs, so the absolute value of this thing would be the gap. And in particular, note that the bulk band structure is actually the same for t minus t primed is equal to either plus or minus this gap delta. So you cannot tell the difference from the band structure, the bulk band structure, whether or not t primed is greater than t or t primed is less than t. And this makes physical sense from our physical picture of the lattice. in the bulk, every site is connected to one strong bond and one weak bond. If we swap over the definition of the strong and weak bonds, we still get the same physical picture. Note also that if T is equal to T primed, then there is no gap, and we have a metallic system, so there's no gap between the two bands. And of course, we know that that's correct, because if T is equal to T primed, we have a sort of uniform, homogeneous chain with no alternation in the coupling strengths down the chain. And that's a case we already studied, the one-dimensional quantum wire, and we know that that's a single band problem, which is a metal. So the fact that this gap vanishes as T minus T primed makes eminent good sense. Okay, so basically the band structure I can now sketch. So this is the bulk band structure, and what I'm going to plot here are the eigenvalues, and I'm going to plot them as a function of k. Pi will be in the middle, 2 pi will be here, and I have two bands, and depending on the parameters, it's going to look something like this. For one of the bands, that's the one at positive energy, so that's lambda plus, and then one of them at negative energy. It'll look something like this, and that's lambda minus. And when I was talking about the minimum gap, what I mean, of course, is precisely this gap here, which is exactly delta. That is the minimum distance between these two curves, which, as we correctly identified here, happens at k equals pi. So importantly, what we see here is that there's a range of energies lying inside this gap for which there are no states at all at any momentum. And of course, that's what we mean by a gapped system. This is an insulator because we have two bands, this lower one and this upper one, the valence bands and the conduction bands, if you like, which have a continuum of states, meaning if I look at energies anywhere in this range, I will have some states sort of crossing that line, likewise up here, but in the middle there are no states. So this is a classic band insulator. Okay, so one final thing, let's just write our Hamiltonian finally in this diagonal form. It's the sum over momentum k. We'll say it's the sum over bands, let's call it alpha is equal to either plus or minus. And then we have the dispersion relation, which tells us how the momentum is connected to the energy for each of the bands. That's a function of k. And then we have a completely diagonalized system now, f alpha k dagger f alpha k. So this is the fully diagonalized form. So I've introduced these diagonal operators in momentum space now, f alpha k. How do they relate to the c k's? Well, if we imagine writing a vector of the f's, which are just f plus and f minus, then we define that the ck vector is some matrix U times the f's, following exactly the usual logic. These are fk's, of course. And we define the U such that U dagger M U is precisely this matrix of eigenvalues, lambda plus, lambda minus. So we actually sort of did this shortcut cheat here to work out the eigenvalues without actually working out the matrix U. So we didn't explicitly work out the transformation, but we did obtain the band structure. So let's now just plot the band structure properly, rather than making cartoon sketches. I'll do this in the package Mathematica, and we'll see what happens as we vary t and t primed. Okay, so here we have a Mathematica notebook in which I'm plotting the two eigenvalues as a function of momentum, k, from 0 to 2 pi, and we have two distinct eigenvalues. Here we have two tunneling parameters, t and t primed. I'm setting t primed equals to 1, and the inter-cell, the coupling between the different cells, I'm changing this. So When it's equal to 0, we have no dispersion because we have separated dimerized unit cells. But as I increase the t, I see that these bands pick up a dispersion, and there's an energy gap between the two bands that's basically equal to t minus t primed, which therefore closes when t is equal to t primed. And then we basically have two superposed cosine dispersions, as you might expect for a homogeneous chain. But as I increase the t further, we see that the gap reopens again, and notice in particular that there's very little distinction. One can't really tell whether t primed is greater than t or t is greater than t primed. The dispersions look basically the same. So now I would like to consider the so-called topological invariant, or winding number in this case, for the SSH model. So we'll see the full physical interpretation of this quantity in a moment, but for now I just want to express the Hamiltonian in a particular way and calculate from it a particular quantity, which will be this winding number. So let me write down the Hamiltonian again. And I'm writing this in the original basis of the C operators with this matrix M. And here I've used the fact that e to the I theta is equal to cos theta plus I sine theta by Euler's formula to write this in a little simplified way. And it turns out that I can write this matrix M in terms of the so-called Pauli matrices in the following way. This is simply equal to t primed plus t cos k of sigma x minus t sine k of sigma y. And here are the Pauli matrices written out. So, of course, the Pauli matrices here, together with the 2x2 identity matrix, form a basis for the real vector space of all 2x2 complex Hermitian matrices. And what that means, of course, is that we can express any matrix we like in terms of a linear combination of these Pauli matrices. And it's particularly simple in this case, and we just read off the solution here. We can express these pieces with the plus sign in terms of sigma x, and the pieces with the relative minus sign on the off-diagonal in terms of sigma y. We can also introduce a vector of Pauli matrices, which is denoted sigma vector, and that just has components sigma x, sigma y, and sigma z, as you might expect. But it's a bit of a funny object because this is a vector of 2x2 matrices. And using this representation, we can actually write the matrix M, which is a function of k, of course, momentum k, as some vector d of k dotted into this vector of Pauli matrices. And in this case, it's easy to read off what the vector d of k is. The vector d of k is simply t primed plus t cos k minus t sine k, and then 0 in the Pauli z direction. So this is a nice compact way of writing these kinds of matrices. And one final thing we can do is consider a normalized vector which let's call it n of k for normalized. And that's just the vector d of k divided by its length, the magnitude d of k. So if we work out this magnitude here, we just use Pythagoras' theorem to look at the square root of the sum of the squares of these components sitting inside the vector there. And what we actually find when we do that is that this is nothing other than the dispersion, lambda of k, that we previously wrote down. and this is the dispersion written out again. So previously, of course, we had two eigenvalues of the fully diagonalized system, lambda plus and lambda minus. They are just this function lambda here with a prefactor of either plus or minus for either the plus or minus band. Note also that at t primed equals t and k equals pi, we have a bit of a problem here because lambda k would be equal to 0. But if we consider any other point for any t primed not equals to t, then this prescription is perfectly good. So here is the bulk SSH Hamiltonian written out again in terms of our vector d. So this vector d is something that we can plot, and let's see what it looks like for different choices of parameters. So we can plot d of k in the xy plane because the z component is just 0. What are we going to be plotting here? Well, we can see from this expression that d of k is a circle centered on x equals t primed, y equals 0, and the circle is of radius t. And then as we increase k, we go around this circle. So let's remind ourselves of these parameters t and t primed. So t primed, the way we've set the problem up, is the coupling within the unit cell whereas t is the coupling between unit cells. And as we'll see, it actually matters which of these is stronger than the other. If t primed is greater than t, we form dimers within the unit cells, whereas if t is greater than t primed, we form dimers between the unit cells. So with this in mind, let's now plot this vector d of k. We see that, of course, there is no z component of this vector, so we can just plot it in the xy plane as a function of k. So let's plot d of k on this figure. I've marked here the center of the circle that this vector will trace out, located on the x-axis a distance t primed away from the origin. That's what we see here from this term. So at k equals 0, we start off at this point, let's say, and then as we increase k, we move around the circle in this fashion. So this is not a very well-drawn circle, but you get the idea. And we move around like so. And the point is that at every point along this circle, we have this vector to a particular point here, let's say, and that vector is precisely this vector d at a given k. And so that point traces this around this circle centered on t primed 0. So that's the situation for t primed greater than t. That means that the circle that is traced out does not encompass the origin of our coordinate systems. It does not encompass the point 0, 0, because the radius of the circle is, of course, this distance here, and the radius of the circle is t. So if t primed is greater than t, the circle does not encompass the origin. Let's have a look at the alternative scenario. In this situation, we have t greater than t primed. The coupling between the unit cells is greater than the coupling within the unit cell. Again, I'll plot the center of the circle here on the x-axis, a distance t primed from the origin, but this time, because t is larger, at k equals to 0, we start off over here, and then we trace out a circle. Again, this is a pretty bad diagram, but the idea is hopefully clear. We increase k from 0 to 2 pi, and we go around the circle like this. And the important point is that this time the circle does encompass the origin. So the distinction between these two cases is encoded in the so-called winding number. And if you delve further into this subject of quantum topology, you'll see there's all sorts of winding numbers or integral invariants, topological invariants, which characterize different phases of matter. And this is a very simple system with a very simple winding number, but you'll see lots of integral invariants like this cropping up in this field. So the one of relevance here, let's call it nu, is an integral over the whole Brillouin zone, meaning all of momentum space, integrating over k, of the z component of this cross product of the normalized unit vector n with the momentum derivative of that vector. And let me just remind you that this n of k vector is just the d of k vector that features in our Hamiltonian, normalized, so divided by its length at every point in k. So this looks like a bit of a funny object, but this kind of thing features a lot all over the place in topology. And the idea is it's something that encodes non-local information about the system because we're integrating over all of momentum space. And what you find when you compute this object, and I'll leave that to you as an exercise to do the maths of it, it's rather simple. You just take d of k over here, you normalize it, you take the derivative and form this cross product, and then take the integral. It's just a simple integral in the end. So I leave that to you, and what you'll find is that this object takes two distinct possible values. It can either be 0 or 1. When it's 0, we call this the trivial phase. Whereas when this winding number is equal to 1, we have a topological phase. And when you go through this process, what you'll find is that the trivial phase pertains when t primed is greater than t. This is when the coupling within the unit cell is stronger than the coupling between the unit cells. Whereas the topological phase with a winding number of 1 is obtained when t is greater than t primed. The coupling between the unit cells is stronger. And this winding number is basically picking up this difference about whether or not this vector is encompassing the origin or not. So the trivial phase is when it does not, t primed is greater than t, and the topological phase is when this tracing of this vector d does encompass the origin, and that's what we see in the topological phase for t greater than t primed. And the interesting thing about these kind of topological invariants, these kind of winding numbers, is that it doesn't matter what t and t primed are, as long as t is greater than t primed, we'll be in the topological phase. And that's because we'll always encompass the origin precisely once. Whereas, if t primed is greater than t, we never encompass the origin. And so there's a distinct difference between these two things on this mathematical level. However, you might be wondering what the physical difference is between these two phases. After all, we're considering the bulk system here. This is the bulk Hamiltonian, and we have a full sum over momentum space k. So we have a translationally invariant system, a periodic system that goes forever in real space, and we have a continuum of k in momentum space. So if we look in the middle of the bulk of this SSH chain, each site is coupled on one side to a strong bond, on one side to a weak bond. If we swap over t and t primed, going from t being the greater to t primed being the greater, then in the bulk we still have the same situation. Every site is coupled on one side to a strong and one side to a weak. So what is really the physical difference? I mentioned before, when we were looking at the spectral function, the density of states, that we can't tell from the single particle band structure whether or not t primed minus t is plus delta or t primed minus t is minus delta. They look identical in the bulk. So what really is the difference here? And actually this comes to the heart of what these topological systems are all about. We actually have to cut the system and think about what happens at the boundary. What happens at the end of the chain? And there we see there is actually a big difference between whether or not we're in the trivial or topological phases. And that's what I want to consider now. So here is the Hamiltonian again for the SSH chain, written down in the form of a 1D chain of unit cells. But this time, notice that I'm including a finite sum over the unit cells. So instead of being an infinite system, I now start the chain at unit cell x equals 1, and then the chain goes on and it has a finite length of n unit cells in total. So the important point here is that the chain terminates and there are two n's, one at x equals 1, one at x equals n. Let me remind you of the matrices that feature in this equation. There's this matrix E, which is the matrix describing the coupling between the A and B sites within a unit cell. And then there's the matrix T, which describes the coupling between unit cells. And in particular, I couple a B site in unit cell X to an A site in unit cell X plus 1, and then vice versa, contained in this Hermitian conjugate term here. So previously we considered a bulk system or an infinite system. These similar kind of properties can also be considered by periodic boundary conditions of a finite chain, but here we have an open system. With open boundary conditions. Here, of course, my vectors Cx describe the two orbitals in the unit cell. So in unit cell X, I have sites A and sites B. But I could also write this Hamiltonian just as one giant matrix in this way. Let's call the matrix A in question, where this vector of operators C now just contains all of the operators in the system. So starts at unit cell 1 with orbitals A and B, and then there's unit cell 2 with orbitals A and B, unit cell 3 with orbitals A and B, and so on. So this vector will actually contain all of the operators in the system. So this vector here is a vector of length 2n. We have n unit cells. There are 2 sites per unit cell. And so this matrix here is a 2n by 2n matrix. And that matrix looks like this. So we have zeros on the diagonal. That would be where the energy or chemical potential would go. And then we start off the chain with T primed, then the next tunneling is T, then it alternates to T primed again, and so on. So we have a tridiagonal structure with alternating parameters here. So something like this, and then everywhere else gives me zeros. And actually, I can break this matrix down into blocks, so I can consider 2 by 2 blocks like this. Let me just divide it all up into the unit cells. So something like this. And then you can see where these matrices E and T come from. So this actually has a tridiagonal structure, but a block tridiagonal structure. So if I fill in the sort of zeros here, you can probably see that this 1D chain can be broken down into a sort of tridiagonal structure like this. So we can write it just as like a regular 1D chain with E's on the diagonal, something like this, and T and T transpose, or T dagger, in the off-diagonal or leading off-diagonal elements, and then zeros elsewhere, where this is like a matrix of these individual 2 by 2 matrix blocks. So E here is this 2 by 2 block, T is this 2 by 2 block. And so this has the usual structure of a 1D chain, a tridiagonal matrix, but it's broken down into unit cell space. And we sort of get the equivalence between these two pictures. And of course, the general strategy is that we can now diagonalize this matrix A. And the way we do that is to define a new set of operators F through some unitary transformation U, such that U dagger AU is a diagonal matrix. And then we can write the Hamiltonian in terms of these F operators with some diagonal eigenenergies, which are these epsilon j's. So let's have a look again at the numerical solution of the open SSH chain with a boundary. So I'll just compute the eigenvalues for this system and show you what happens with Mathematica. So let's see that now. So this time I'm using the Mathematica code to implement our two matrices E and T and to generate the full matrix, which you can see has this tridiagonal structure with epsilons on the diagonal and then the tunneling parameters within the unit cell T1 and between the unit cells T2 on the leading diagonals. So this bit of code just generates that, and then we can numerically diagonalize that matrix to find the single particle levels. So in this plot, what I'm showing is the eigenvalues, the energy eigenvalues plotted on the y-axis, just sort of enumerated along the x-axis. So the x-axis doesn't mean momentum or anything, it's just an index for the number. And we see that there are two unique groups of eigenvalues at plus and minus 1 when we set T1 to 1 and T2 to 0. But as we increase the T2, we see that all the sites in the system become coupled, and we have some dispersion to the eigenvalues. So we see that there's still two bands, and those bands actually then close as T1 becomes equal to T2, and we get a single band. So there was a band gap for finite T1 minus T2, but as T1 equals T2, we get a single continuum band between energies minus 2 and plus 2. All eigenvalues fall into this property. But then as I increase T2 further, so now the system starts with a weak bond rather than with a strong bond at the end, we see that there are two bands and there's a band gap, but there's also two states left exactly in the middle at zero energy. And those states don't appear to be perturbed as I change T1 and T2, provided that we start with a weak bond. As I go to the strong bond, I lose them again. So let's have a look now at the lowest energy eigenvalue. So as a function of the difference between T1 and T2. So when we start with a strong bond, we see that there's a rather appreciable finite energy to the lowest energy eigenvalue. So when delta T, the difference between T1 and T2, is equal to 0.1, we see a large value. But as I decrease the difference, the lowest energy eigenvalue decreases, as you might expect for the gap closing. But as I make delta T negative, therefore starting with a weak bond, I see that the lowest energy eigenvalue becomes exponentially small. The energy goes very, very close to zero, exponentially close. So this can also be visualized by plotting the whole range of energy eigenvalues as a function on the x-axis here of T2 as for a constant T1. We see that for T2 equals 0, again we have the dimerized limit, just all the energy eigenvalues are either plus or minus 1, but as I increase the T2, these split into bands. But notice importantly, of course, that this lowest energy eigenvalue kind of pairs off and then remains stuck at 0 in the topological phase. So what we saw is that in the case where we have t primed less than t, we have these zero energy states in the spectrum. So t primed less than t gave us actually two zero energy eigenstates. And when I say they're zero energy, the energy of those eigenstates is exponentially small. It's exponentially small in the length of the chain, and it's exponentially small in the size of the band gap in the SSH model. I'll come back to that. And if we look at the case t primed greater than t, there's a hard gap in the spectrum, and that means no zero energy states. Let's call them zero modes. And of course, if we go back to our previous discussion of the winding number and topological invariants, we know that this first situation is precisely the topological case. Whereas this one, with no zero modes, is the trivial case. So let's have a closer look at what these zero energy states actually are. Of course, we have the numerical solution to hand. By diagonalizing the matrix A, I have basically found the matrix U that performs the diagonalization, and that matrix U is a matrix of the eigenvectors. Those eigenvectors, of course, tell us what is the amplitude on real space orbitals of a given eigenstate. So let's just have a look at the eigenstates that have zero energy and see what they look like. What is the structure of those eigenstates in real space? So let's have a look at that now. So what I want to plot here is the wave function, the amplitude of the wave function on the y-axis as a function of the site index along the chain on the x-axis. And you'll see here that I have 100 sites in the chain. So we have the wave function amplitude versus site index. And I'm going to do this as a function of delta t, meaning the difference between t1 and t2. And I'm starting off here with delta t equals to 0, which means the fully homogeneous chain where there's no alternation. And I'm plotting the lowest two energy eigenvalues. So this is the metallic case shown here. We have wave functions that are totally delocalized over the entire system. As I increase delta t, whilst still staying with a strong bond at the beginning of the chain, I see that these wave functions evolve somehow. However, they remain delocalized over the full system, and you can see the energy list at the bottom there is still finite. However, as I go into the topological phase for negative delta t, meaning the chain starts with a weak bond, I see these lowest energy eigenvalues, the energy of which becomes very, very small, take on a rather different form. They become exponentially well localized at the edges of the system. These two eigenstates, one at each end of the chain, become very, very well localized, exponentially localized. They're not delocalized. They only become delocalized as I go into the trivial phase. In the topological phase, they're very well localized. So we saw that in the topological phase, t primed less than t, we have zero energy eigenstates, and when we look at the wave functions of those things, or the square modulus of those things, which encode the probability density of finding an electron at that site, we find that the state is exponentially localized, and it's localized at the edge of the system. So this wave function profile here goes as e to the minus n over xi, where n is the chain site index, and this xi is a localization length. And we'll come on to deriving that explicitly in a moment. Whereas in the trivial phase, for t primed greater than t, we have no mid-gap states, and all of the states are found to be delocalized and spread out over the entire system. Here's just one example. So how can we understand this effect? Well, first of all, let's consider an extreme limit. And this is going to be the limit with t is equal to 0, but t primes will remain finite. So this is a dimerized limit. And let's just draw a little cartoon showing what's going on here. The chain starts at unit cell number 1, and that consists of a dimer. But because t is equal to 0, that is completely disconnected from the neighbouring unit cells, and so the whole system factorizes into this sort of product of these isolated, disconnected dimers. And if we want to know the eigenstates of this system and eigenenergies, then it's completely trivial, because each of these dimers doesn't in any way couple to its neighbours, and therefore all we need to understand is the bonding and anti-bonding orbital of the dimer. The bonding orbital lies at minus t-primed energy, the anti-bonding orbital lies at plus t-primed energy, and we have a high degeneracy of those states. If we have n unit cells in the system, we will have n states lying at minus t-primed and n lying at plus t-primed. And there's no dispersion because there is no propagation of electrons down the chain. So in this extreme dimerized limit, we have a bunch of eigenenergies at plus and minus t-primed. So let's consider the other extreme limit with t primed equal to 0 for finite t. So with t primed is equal to 0, we have again a dimerized limit, almost. To see why it's almost, let's draw again our picture. This time, the bonds between the unit cells are finite, and the bonds within the unit cells are equal to 0. And what we have is again a bunch of dimerized states, except for the ones at the end of the chain. So these ones at the end of the chain here are special. They are completely decoupled from the rest. And so what we have is n unit cells, and this actually gives us n minus 1 dimers. That gives us n minus 1 states at an eigenenergy of plus t this time, and n minus 1 states at an eigenenergy of minus t. But we also have two states, which are the ones I've highlighted, at exactly 0 energy. And they're at 0 energy because they're decoupled from the rest of the system. They don't appear in the Hamiltonian anymore. They're totally decoupled. So these edge states, the ones at both ends of the chain, lie exactly at 0 energy, and they're perfectly localized states. The eigenstates will be perfectly localized at the edge of the chain. So this is rather interesting. Even though these are trivial extreme limits, either setting t equals to 0 or t primed is equal to 0, it actually captures the basic essence of what's going on in the full system. In the trivial phase, which is t less than t primed, which encompasses, note, this extreme limit of t equals to 0, we have completely delocalized states and no 0 energy states. The system is completely gapped. Whereas in the topological phase, which is t greater than t primed, which, note, encompasses t primed is equal to 0, we have exponentially localized states living at the edge, living at 0 energy. So this is quite interesting because whilst it's trivial and obvious what's going on in these extreme limits, for finite t and t primed, we see the same phenomena persists, where even when these states living at the edge here are weakly coupled into the rest of the system, they remain exponentially localized, and they remain at exponentially low energy. And that's what we saw in the numerical implementation, just brute force diagonalization of a finite system. So let's now have a look at this from an analytical perspective and actually try to understand more about the localized states, not in this extreme limit, when t prime is equal to 0, but in the regular case, in the topological phase for t prime less than t. So let's have a look at those boundary zero modes in the SSH chain. In particular, we're going to do this using the so-called transfer matrix method. Let's consider one of these zero energy eigenstates. And I'll denote this by this wave function ket 0, and the 0 is meant to indicate that it's a zero energy state. And I want it to be an eigenstate of the full system. So it's really an eigenstate of the SSH Hamiltonian. And of course that means it satisfies the Schrödinger equation. Which is that H acting on psi 0 gives me the energy times psi 0, but the energy is 0. So I have this interesting condition, and actually we're going to use that condition together with the 1D structure of the Hamiltonian to determine properties of this state. So as a totally general ansatz, we'll let this psi 0 be equal to, let's say, the sum over y over the unit cells labelled by y of some parameter for the A sites in unit cell y times the creation operator for an A orbital in unit cell y plus some parameter for the B orbitals in unit cell y. And this will act on the vacuum state, which is the completely empty state. So this is a totally general ansatz for the kind of state that psi 0 can be. It's a single particle state, as you can see. That's the kind of thing that we want to obtain from this analysis. And it's parameterized simply in terms of these coefficients, uay and bay, which tell us the magnitude in the superposition of states of the A orbital and the B orbital in a given unit cell y, and then we sum over all the unit cells. So let's remind ourselves also of the Hamiltonian, which I'll just write in the most basic fashion. So this is the Hamiltonian specified in terms of operators which are for a given unit cell x and an orbital A or B within that unit cell. So let's now simply apply this Hamiltonian to this state, and then from this expression for the Schrödinger equation, we see that that's all equal to 0. In particular, we're going to end up with a double sum over x and y, because the Hamiltonian contains a sum over x, and the state itself includes a sum over y. So when we apply one to the other, we're going to have a double sum. It's a bit messy, but the algebra is straightforward, so let me just write it out. So after a bit of writing, we obtain this following expression, which looks like a bit of a mess. In particular, we have 8 terms, because we have 4 terms in the Hamiltonian, each of which get paired with the 2 terms in the expression for the state. And I've been careful here to denote the A and B sites in the unit cell, and whether I'm talking about x and y from these 2 different sums. So this expression tells you about the Hamiltonian being applied to this eigenstate. We can write it in terms of this bunch of operators acting on the vacuum state. And importantly, we know from the Schrödinger equation that this whole thing must be equal to 0. So we can analyse this expression a bit more because we know that these various operators that feature in this whole gamut here are applying to the vacuum state, which is something which is completely empty. And so we can actually get rid of a bunch of these terms right away. They have to be equal to 0. For example, if we consider this term, I am creating a particle in unit cell y orbital A, but then I'm supposed to destroy a particle in unit cell x and orbital B. And because we're talking about different sites, this one is an A site and this one is a B site, I cannot destroy this electron because there's already nothing there in the vacuum state. And that logic goes for all of these terms that feature an A being created and a B being destroyed, or likewise a B being created and an A being destroyed. We can't destroy anything if it's not already occupied, and the vacuum state is totally unoccupied. And so what this means is that this term must be equal to 0, and by the same logic, this term must be equal to 0, because again, we're destroying in the A site, and there's nothing there, and we can really go through and strike out half of the terms using this logic. What else can we say? Well, let's consider this term, for example. Here, we're creating an electron in unit cell y, orbital B, and then we're destroying an electron in orbital B, but unit cell x. And so this has a possibility to be finite if x and y are the same unit cell. Then I create an electron in a unit cell, orbital B, and I destroy the same electron. That's allowed. But that can only happen if x and y are the same. And so this term must come with it a delta function, delta xy, only if x and y are the same. Likewise, here there must be a delta function of x and y collapsing the sum. Here, I see the same logic. But in this final term, I have something slightly different. I must have that x plus 1 is equal to y for this term to be finite. And so that's a slightly different kind of term. So this has with it a delta function of y and x plus 1. And I can use all of these delta functions to collapse this double sum over x and y to a single sum over x, and I obtain then the following set of terms. So tidying all of this up and collapsing that sum using those delta functions and so on, I get the following collection of terms, and these have now reduced to single creation operators, and these are all acting on this vacuum state. Notice that I do have operators acting in unit cell x plus 1 in this sum, and I also have coefficients for unit cell x plus 1, but they are associated with different terms. And of course, the whole point is that we know from the Schrödinger equation that all of this has to be equal to 0. So I can actually look at this term by term. If I act with CAX dagger on the vacuum, I'm going to create a single particle state with a single electron in unit cell x, orbital A. The only way that this total sum can be equal to 0 is if there's another term in this sum that exactly cancels out that thing. The only other term that can do that is this term, because that's the only other term that acts on orbital A. And we see here that this actually is creating an electron in unit cell x plus 1. But since I'm summing over all x, these have the possibility to cancel. One from a given x, the next one from the neighbouring x. And that gives us a condition that t primed u bx must be equal to minus t u b x minus 1. By the same logic, if we compare the terms with operators acting on the b orbitals, then we get this condition. We get that t primed u ax must be equal to minus t of u a x plus 1. So let's consider what happens in the first unit cell. Let's let x equals 1. The problem with this condition is that t primes of UB1 would have to be equal to t of UB0, but there is no 0 unit cell. And what this tells you is there's no way to cancel this first term. Because the chain begins at unit cell number 1, there is no way that we can cancel this operator acting on the vacuum for the first unit cell of the system. Or another way to say it is that we have a unit cell 0, but the coefficient that accompanies it is equal to 0. Either way, this condition actually implies that if the Hamiltonian acting on this wave function is to be equal to 0, then the coefficient UB1 must be equal to 0. And if UB1 is equal to 0, then that means UB2 must be equal to 0 through this relation. So we simply put x equals 2 in this expression, and that relates UB2 to UB1, and we've just shown that UB1 is equal to 0. And so by this logic, what we learn is that UBx is actually equal to 0 for every single unit cell in the system. So this is rather interesting. It tells you that the wave function of the zero energy mode has 0 amplitude on all of the b orbitals. Actually, this is related to a certain chiral symmetry in the problem, but I don't think we'll get into that now. So that's rather interesting. Now, of course, the wave function can't be totally 0, it has to normalize to 1, and so that must imply that these coefficients can be finite, and of course they can be finite, and that's precisely because we can get this term in our series to cancel with this term, and this involves comparing unit cell x and x plus 1. So again, if we were to let x equals 1, then we simply find that t primes of ua1 is equal to minus t of ua2, and both of those can be finite. In fact, if ua1 is finite, then we can know what ua2 is, and if we know what ua2 is, we can work out ua3, and so on. So overall, this gives us a recursion relation which tells us that ua x plus 1 is equal to minus t primed upon t of uax. And of course, we can then just repeat that procedure to find an arbitrary coefficient uax in terms of ua1. And the coefficient is going to be minus t primed upon t to the power of x minus 1 of ua1. So for example, if I were to put in x equals 1 here, this would be this to the power of 0, so ua1 would be ua1. However, if I want to know ua2, then I get 1 power of this factor. If I want to know ua3, then I get 2 powers of the factor, and so on and so forth. So what we've shown using this transfer matrix method is that the amplitude of the zero energy eigenstate is exactly 0 on all of the b sites, and it has this exponential form on the a sites. And very importantly, we saw that the zero energy states only exist when t primed is less than t, when the chain begins on a weak bond. And what that means is that if t primed is less than t, then the magnitude of this ratio is less than 1. And so as I raise it to this power, that magnitude gets smaller and smaller and smaller, meaning that these coefficients become exponentially small as I move away from the boundary or edge of the chain. So let's have a look at the wave function amplitude, and we'll see exactly what happens. So here is the zero mode wave function amplitude on the a sites, and we can really interpret this as the probability density of finding the electron on a particular real space site on the chain. And of course, the way we've written it, it now depends on this initial amplitude. And this looks like it's not yet in closed form, But we actually also have another trick up our sleeve. Of course, it's the normalization of the wave function. So the normalization condition tells us that if I sum up all of these amplitudes over all x, that has to equal 1. So with these two expressions, I now have everything I need to determine uniquely the initial wave function amplitude on site A1, and then with that in mind, I can then calculate all of the other ones. And of course, the zero mode only exists for t primed less than t. Another way of seeing this is to say, if t primed was greater than t, then this expression here would tell us that the wave function amplitude was exponentially growing into the chain, and that would not produce a normalizable wave function, and therefore no such zero energy state could exist. So our initial assumption that we had a zero energy wave function, which was an eigenstate of this system, would have to be proven incorrect. Whereas for t primed less than t, we see that this expression is exponentially decaying with x, and we can normalize the wave function. So we've basically been able to prove that there is an exact zero energy state in the topological phase for t primed less than t. We had an ansatz for a particular kind of wave function, we plugged it in, and we showed that it does satisfy the Schrödinger equation if this equation is satisfied, and that equation can be satisfied together with the normalization condition. For t primed greater than t, it is not possible to normalize the state, and so our initial ansatz would have to be proven to be incorrect. There is no zero energy state in the case t primed greater than t. Okay, so finally, let's work out the localization length of the system. That can basically be read off from the exponential decay of the wave function amplitude, and it's very simple to extract. So when we talk about a localization length, this is precisely what we mean. We mean the wave function amplitude goes as e to the minus x upon xi, where xi is the localization length. So now we can just compare this expression with this expression, and of course what we then find is that t primed over t to the 2x minus 2 must be equal to this e to the minus x upon xi, and this gives us a condition to work out the xi. And with a bit of manipulation, we find it to be x over x minus 1 multiplied by a half over log of t over t primed. And in particular, if we go a long way from the boundary, so x much greater than 1, then this localization length goes to basically 1 over the log of t over t primed. And since the ratio of t and t primed control the gap in the bulk of the system, we can see that the localization length is controlled in the size of the gap. Also note that as t primed approaches t, the localization length diverges according to this analysis. So the point is, here we have a localized wave function only when we have a gapped system with t primed less than t. And the amount of localization, characterized by the localization length, is controlled in the gap size. So to substantiate this, let's go back to the numerical calculation and show that the zero energy eigenmodes in the topological phase are indeed exponentially localized. So let's move on to the second type of model that I want to discuss in today's lecture. It's the so-called Kitaev chain. This has some unusual properties that are rather different from the SSH model, but some of the basic ideas are the same, so we're not going to go over it in exactly the same kind of detail, but I will highlight some of the key differences. And that, of course, starts right from the Hamiltonian itself, which does take a rather different kind of structure. The Kitaev chain Hamiltonian takes the form of two terms. The first term is a very, very simple, homogeneous 1D type binding chain. There's no alternating hoppings, there's no spin, there's no interactions. This is a very, very simple 1D type binding chain. However, there is an additional term which corresponds to superconducting pairing. So this is an unusual kind of term. It involves the pairing of electrons on neighbouring sites. Again, this is a spinless system, and what we see here, for example, is that we create two electrons, one on site x and one on site x plus 1. So this is, see there's two terms here, both with daggers. So usually we're used to seeing one creation operator and one destruction operator. Here is a pair creation. And for the Hamiltonian to be Hermitian, we need to include the Hermitian conjugate of this term as well, and that's this one, which destroys a pair of electrons. So here we're creating a pair of electrons on neighbouring sites or destroying a pair of electrons on neighbouring sites. And manifestly, this Hamiltonian does not conserve charge, but it does conserve the parity of the charge. So whether or not we have an even or an odd number of electrons is conserved, but the actual number is not conserved. And the way of thinking about this kind of Hamiltonian is that it's an effective mean field kind of Hamiltonian. It's the so-called BCS type Hamiltonian, describing superconductivity. So what we imagine is that there is a condensate of these Cooper pairs, and that condensate is not written in this Hamiltonian. Instead, we just consider an effective Hamiltonian where pairs of electrons in our system can condense, can bind together and drop out into the condensate, and then they vanish from our system. So we consider like a system and an environment. Here is a Hamiltonian just for the system, and we can lose or gain pairs from the environment, which is encapsulated by this term here. And in this system, I also want to add a chemical potential term, so I'll just add mu lots of the number operator on each site. We'll see that the interplay between T, delta, and mu is rather interesting in the system. So first of all, let's consider the bulk of this system. And what I mean here is we're going to consider an infinite system, or one with periodic boundary conditions. How do we perform a Fourier transform on such a system? Actually, it's not completely straightforward, because normally we rely on having a quadratic form to the Hamiltonian with pairs of operators, one of them being a destruction operator and one of them being a creation operator, and we actually don't have that here because of these superconducting terms. The Hamiltonian takes a bit of a different form. So to get around this, we're going to introduce a vector operator, big C, for site labelled by x, and this is going to be a vector which actually features both the annihilation operator for site x and also the creation operator for site x. Likewise, we have big C dagger vector, which is going to be the conjugate transpose of this, so it's going to be a row matrix with Cx, dagger, and Cx. And these are called Nambu operators. So these big C vectors are not fermionic operators, they are vectors of fermionic operators, one of which is a creation operator and one of which is an annihilation operator. And it allows us to write our Hamiltonian in the following form. And for good measure here, I'm going to introduce an overall factor of 1/2 out the front, and I'll also add on a constant. This constant at the end doesn't matter at all because this is the Hamiltonian, it's controlling the dynamics, so any constant term there, rather than operator, is just a constant shift to the overall energy, which has no effect. So implicitly I'm having a constant here, but I'm now going to forget about it right away. But just bear in mind that when I'm comparing these two Hamiltonians, they'll actually only agree up to the value of this constant. So now I want to determine these matrices E and T, which are 2x2 matrices, and I can do that by comparing this Hamiltonian with this Hamiltonian. And when I do that, I get the following. So it's worth spending a bit of time to unpack this and make sure that we understand it. Let's just write out the Hamiltonian in this basis for a couple of unit cells. We'd have something like Cx dagger Cx, and then the matrix E, which is mu 0, 0 minus mu, and then the vector C, which gives me Cx and Cx dagger. So that's one of the terms. And let's just try to understand what's going on with that. If we expand it out, we would get the following. We'd get mu lots of Cx dagger Cx minus mu lots of Cx Cx dagger. So this is a slightly unusual term, but of course these are fermions, these Cx's, and therefore we can simply use the anti-commutation relation to reorder these operators, and that would give us 2 mu Cx dagger Cx minus mu. And I get the minus mu from the anti-commutation relations, because we're talking about the same site after all. Okay, so now we see two things. One is to be able to compare these two equations properly. Here I'm getting a factor of 2 mu. That's why I actually introduced this factor of 1/2 out the front of this equation to cancel that. And secondly, because of all the anti-commutation relations, we're going to pick up a load of these constants minus mu here, and that's exactly what this constant is supposed to be. That constant just cancels this. After this, I'm just going to forget about that constant term. It doesn't make any difference. Okay, so what about the terms involving the t and the delta? There I have this kind of stuff. I have a Cx dagger Cx vector with my matrix T, which is T delta minus T, and then Cx plus 1 and Cx plus 1 dagger. And so what happens when I expand all of this out? Well, I get the following. So here we see two terms involving the hopping T and two terms involving the superconducting pairing delta. And again, we can use the anti-commutation relations to reorder some of these operators. In particular, I can change the order of these two, and that will just give me a minus sign. And I can also change the order of these two, giving me a minus sign. And then I will see that here, in this term, I'm actually getting twice of the original tunneling term that I want, again, hence the factor of 1/2. Whereas for these second two terms involving delta, by reordering them, I get precisely these superconducting terms. And if I finally consider this term, I won't write it out again, but it's pretty easy to show that I reproduce the original Hermitian conjugate term in the hopping piece, and again recover the same piece here, again, hence the overall factor of 1/2 in the Hamiltonian. So it looks a bit weird, but this is a rather neat way of writing the Hamiltonian. In particular, the structure of this Hamiltonian, written in this Nambo formalism, looks exactly like a type-binding 1D chain with a two-site unit cell. Of course, we don't have a two-site unit cell here, it's just that we have two objects in our vectors, which are the creation and destruction operators. So although the mathematical structure looks identical to, for example, the SSH model, the objects inside these vectors actually are different things. But that doesn't stop us from going ahead and doing the Fourier transform to diagonalize this system, because it has the same mathematical structure. So let's just go ahead and do that. So let's do the Fourier transform of the Hamiltonian that we've written down here in this Nambu space. And the way we do that, as always, is to let our operator Cx, which is a vector operator, also in this Nambu space, be related to these Ck operators with the Fourier coefficients e to the I kx, where we've now introduced momentum space Nambu operators, which are going to be CK and CK dagger. And I've assumed that there's n sites in the system in total, with n going to infinity in the end for our infinite periodic system. And as usual, we can define CK vector dagger simply as the conjugate transpose of our CK vector. So we substitute this into our expression and use the usual identity from Fourier series for the Kronecker delta, and we obtain the following simplified expression, where this matrix M is a 2 by 2 matrix containing the effective dispersion, and that's given by, which follows along very similar lines to what we were doing with the SSH model at the beginning of this lecture. Since we know the forms of E and T, let me just write this out in full as a 2 by 2 matrix. So this is what we get in terms of the parameters mu, t, and delta of our original model. And we notice that here we can replace a few of the exponentials by coses and sines, because cos theta is of course a half e to the I theta plus e to the minus I theta, and sine theta is equal to a half of e to the I theta minus e to the minus I theta. And so we can use those identities to simplify this up a little bit, and we obtain this expression. So we see that we've managed to basically diagonalize the Kitaev chain by going to momentum space in terms of the unit cells, if you like. The unit cells, however, are comprised of these creation and destruction operators, and the remaining matrix that we have, M of k here, is not yet completely diagonal. So we have, as usual, one more step to perform to completely diagonalize the Hamiltonian. So following on from the analysis in the previous part of the lecture, we now know that we can rewrite this in terms of the Pauli matrices in a very simple way. It's mu plus 2t cos k times Pauli z. That accounts for these diagonal terms that are related by a relative minus sign. And then for the off-diagonal components, there's also a piece that goes as minus 2 delta sine k times Pauli y. And that accounts for these off-diagonal terms that also have the relative minus sign. And therefore, we can also write this in terms of our vector d of k dotted into the vector of Pauli matrices, where d of k now can be read off as 0 in the x component, minus 2 delta sine k in the y component, and then mu plus 2t cos k in the z component. So I will leave it to you to have a little think about how to plot this object and what are the consequences following our similar line of argumentation for the SSH model as to when this system would be topological or not. So this is as far as we've got so far. We've got the Hamiltonian for the Kitaev chain in this almost diagonal form after Fourier transforming, where we have these Nambu operators, and this M of k is this non-diagonal object. Actually, we're going to play exactly the same trick that we did when looking at the SSH model. Instead of looking at M of k, let's have a look at M squared. And it turns out that this is extremely simple. Again, it's a diagonal matrix. More than just a diagonal matrix, it's actually proportional to the identity matrix. And we get this in this case. So this identity matrix here is the 2 by 2 identity matrix. So all of the k-dependent dispersion here is in this prefactor. And again, using the same ideas as last time, we know that the eigenvalues of the matrix M squared are just the square of the eigenvalues of the matrix M, and the eigenvectors are the same. And so this is a nice, easy way of working out the dispersion. And this is what we have in the end. We have fully diagonalized the Hamiltonian. Notice that we have a sum over two bands. Alpha is plus and minus, and we have the dispersion here. And the dispersion of the two bands just differs by this plus or minus sign. Also notice that I have written the operators here as these gamma objects, and that's because when we diagonalize the matrix M in this Hamiltonian, we do that by a transformation of our C operators, but our C operators in the Nambu representation involve both the creation and the destruction operators. So when I diagonalize this matrix M, I'm going to take linear combinations of CK and CK dagger, and that's these objects which I'm now calling gamma. So gamma alpha of K will actually be a linear combination, and the exact linear combination also depends on the momentum, of course. So let me call that A of K, lots of the CK operator, and B of K, lots of the CK dagger operator. So these operators, these gammas here, are not simple fermionic creation or annihilation operators, but actually combinations of the two. And that might seem extremely weird, but actually remember from the initial Hamiltonian that we started from, we don't have overall charge conservation due to the superconducting terms. And so, in principle, we can get linear combinations of particles and holes like this. And indeed, quasiparticles, which constitute particle and hole excitations, are actually characteristic of superconducting systems. Okay, so let's analyze this dispersion and try to understand what's going on in this system. Well, first of all, again, we can analyze the point k equals pi, and we'll see that there's the possibility of having the minimum band gap arise for given sets of parameters. In particular, for k equals pi, the sine k term will vanish, and of course cos of pi is -1, so there is the possibility of this piece becoming 0, specifically if we have k is equal to pi and mu is equal to 2t, then we can have that lambda of k equals pi is 0. And we have two bands, one at plus and minus lambda, and so if lambda is equal to 0, we have a band touching point. So the gap closes exactly at this point. If mu is not equal to 2t, then we will have a finite band gap between the plus and minus bands. And you can see also that away from the point k equals pi, this superconducting term here involving the delta will obviously have an effect on the dispersion. But since this term is squared overall, this will always give a finite positive contribution, if it's not 0, to the band gap. So the band gap is basically controlled by this term. So as before, the gap is actually equal to the modulus, or the absolute value, of mu minus 2t. And that occurs, that minimum distance between the two bands occurs at k equals pi. And it's only when mu is equal to 2t that the bands close. So let's use Mathematica again to plot this function as a function of mu, t, and delta, and try to understand what's going on in this system in terms of the dispersion. So what I'm going to plot here with the help of Mathematica is the energy dispersion of these two bands as a function of momentum on the x-axis and energy on the y-axis. And I have three parameters to play with. I have the tunneling between sites on the 1D chain T, I have the chemical potential mu, and I have delta, the superconducting pairing term. And what I've set up here in the first instance is T is equal to delta is equal to 1, but 0 chemical potential. And I actually see something rather weird, which is that the two bands are exactly flat. They have no momentum dependence at all, despite the fact that there is still tunneling down the chain, and I do have superconducting term. Only when I change the chemical potential and make that finite do I start to see a dispersion appearing. And indeed, you see that there's an energy gap which is controlled in the difference between the tunneling T and the chemical potential mu. And if I make the chemical potential equal to the tunneling, T equals mu, the gap closes, and then I have a regular metal. But for any T not equal to mu, then I have a finite gap here, and I have two distinct continuum bands with a gap between where there are no possible states. And then as I move the chemical potential to even higher values, I see that the gap reopens, and again I have two distinct bands with an energy gap. As I play around with the superconducting term, I see that this changes the dispersion, but that the band gap itself is not changed. You see, that still remains the same independently of the delta that I pick. And also the minimum separation between the bands, which controls the gap, is always at k equals pi. Also notice that as I change t, I can make the ratio between t and delta more extreme. I get more extreme shapes. However, if I want to close the gap, I need to set t is equal to the chemical potential. And if I change the chemical potential and I change t, I open a gap, and I've got to readjust t is equal to mu in order to close the gap. So let's now have a look at the Kitaev chain with a boundary. So we're going to look at a finite length of the Kitaev chain and look at what's happening at the ends of the chain. So the mathematical machinery we need for this we've actually already accomplished. It's the 1D chain formulation in the Nambu representation. So this is the Hamiltonian written down in the 1D chain form. Now what we'd like to do for the numerical diagonalization is to form one big Hamiltonian matrix which we can then diagonalize. So I want to write the Hamiltonian in this form. Let's call it matrix A, where this vector operator C dagger here is a vector of all of the operators for the entire system. So this will be C1 dagger C1, C2 dagger C2, C3 dagger C3, and so on, all the way up to the nth unit cell, Cn dagger Cn. You'll see in this Hamiltonian we're considering a finite system. It's a chain with n unit cells. And by unit cell, of course, we really just have n sites in the system. We're just breaking down each site in this Nambu formalism into a creation and a destruction operator. So with that in mind, we can just write down what the matrix A is. It's pretty clear that it will have this sort of block tri-diagonal structure. We have the E matrices on the diagonal and the T matrices on the leading off-diagonal elements. And so on. So this would be an example of the system if I had 1, 2, 3, 4, 5, n equals 5 sites in the system. Of course, the dimension of the matrix is actually 2n by 2n. Because each of these matrices in there is a 2 by 2 matrix. So, in the usual way that we've seen many times before, we're going to diagonalize this Hamiltonian by letting this gigantic vector of operators C be a linear combination of these new operators, gamma, arranged into a gamma vector, such that when we substitute this expression in here, the A matrix is diagonalized through a similarity transformation. So what we want is to define C vector in terms of the gamma vector through this matrix U, such that U is a matrix D which is diagonal. And with that transformation in mind, we can then write down the Kitaev chain Hamiltonian as a set of these single particle states from j equals 1 to 2n. The matrix is of dimension 2n of some single particle energies epsilon j and then gamma j, gamma j. And again, I'm referring to these as gammas because they are a superposition of creation and annihilation operators. So combinations, these quasi-particle excitations corresponds to combinations of particles and wholes. And it is these eigenvalues that I'm interested to look at in the case of a finite system. In particular, I expect to see a certain phase of this model in terms of the parameters mu, t, and delta, where I have exact zero energy modes, and I want to see that those things are localized at the boundaries of the system, and I want to understand what these eigenstates actually are, because of course we will have combinations of particles and wholes, so what does that actually mean physically? So let's have a look again at the Mathematica code, and we'll diagonalize this system, have a look at the eigenspectrum, and see what these zero energy states look like. So in this piece of Mathematica code, I want to consider the Kitaev chain with open boundary conditions. I have a little bit of code here to generate the E and T matrices we were just discussing, and then this code produces the entire Hamiltonian matrix from that, which has this sort of elaborated tri-diagonal or tri-block diagonal structure in the parameters T, the coupling between the unit cells, the delta, which is the superconducting pairing term, and mu, the chemical potential. So what I can do is numerically diagonalize that Hamiltonian matrix and plot the eigenvalues, which are of course the energies. What I'm plotting here is the energies on the y-axis, and on the x-axis is the chemical potential, with t is equal to delta is equal to 1. And what I see is that for mu is equal to 0, chemical potential is 0, I have this dimerized situation, apparently, with two bands plus or minus 2. But as I increase the chemical potential, the gap sort of closes between these two things, and then when mu is equal to 2t, I form the metal, and then as I further increase mu, the gap reopens, and I can see that with the structure of these bands. However, there's something funny happening, because you see that there's actually a zero energy state living precisely at zero energy when mu is less than 2t, and you can see it sort of pairs off from the continuum of states within the band. At the gap closing point, mu is equal to 2t, and then for smaller mu, remains pinned at zero energy. And as we'll see, these zero energy states are actually localized at the boundary of the system. But as I increase the chemical potential, they rejoin the continuum. And to really confirm that these states are really low energy zero modes, we can plot the energy of the lowest energy eigenvalue as a function of chemical potential. And you see that in the metal we have something finite, but as I decrease the chemical potential below 2t, you see this energy becomes really, really small, becomes exponentially small. Even for a finite chemical potential, mu equals 1, something like this, we still see an exponentially small lowest energy eigenvalue in this system. So this is an unusual property, and of course for mu greater than 2t we don't have such a state. That's further confirmed if I just plot all of the energy eigenvalues, as you see here. In the metal, mu is equal to 2t. We see a single band, but as I increase the mu, we have a gap opening to make two bands. There's a continuum set of energy eigenvalues within two different bands and a gap between them. The gap opens as I make the chemical potential smaller than 2t, but two states are left in between. These are those exponentially low energy localized states that I mentioned earlier. So we see this coherent picture. As I reduce the chemical potential, I see two mid-gap states. So what do these states look like? Well, of course, because I've diagonalized the system, I have access to the wave functions, and what's plotted here on the y-axis is the amplitude of the wave function versus the site index along the chain for a 30-site chain along the x-axis there. For large chemical potential, mu is 2t and greater, we see that we have these delocalized states. I'm plotting the lowest two energy eigenvalue states here, and we see they're delocalized over the whole system. But as I decrease the chemical potential below 2t, these states look rather unusual. They become very localized. They become highly localized, in fact, on the edges of the system. So one of the two low energy states becomes localized at the left edge of the chain, and one of them becomes localized on the right edge of the chain. And only when I see the gap closing and forming the metal again do those states become delocalized. So let's now have a look at the famous Majorana representation of the Kitaev chain. So here is the Hamiltonian, again written out just in its simplest form, with its three parameters, one for the chemical potential, one for the hopping down the quantum wire, and delta, of course, being the superconducting pairing term. So what we will do here is introduce new operators, so-called Majorana operators, and there will be a pair of these for each physical lattice site labelled by x. Now we'll call these two operators gamma A on site x and gamma B on site x. Gamma A is going to be a combination of creation and destruction operators, namely it's going to be defined as Cx plus Cx dagger. And then we have an orthogonal combination, which will be defined as 1 over I of Cx minus Cx dagger. And these two are Majorana fermionic operators. Well, what do I mean by Majorana fermions? Well, there's two words, Majorana and fermion, and they both have some meaning. So first of all, let's have a look at the Majorana property. Majorana property tells you that the particle is its own antiparticle, and what that means is that the dagger of the operator should be equal to the undaggered operator. So this is the Majorana property. So the particle is its own antiparticle. Which is a very weird thing. Of course, in these condensed matter systems, the actual constituents, the physical things, are electrons. When I talk about particles here, I'm really talking about quasiparticles. They're the emergent excitations in the many-body system. And these operators that I've written down here clearly satisfy the Majorana property, because if I take this expression for gamma A, for example, written down here, and I take the dagger of it, then we may write that gamma A on site x, dagger is, of course, the daggered operator, and of course this is the same thing. So the gamma A operator satisfies the Majorana property, and similarly for the gamma B. Which is extremely easy to prove. Here we have a little bit of a subtlety because of the definition including this complex I. So when we take the dagger of I, we get minus I. And that's why, of course, this one also works out. However, these gamma Majorana fermions, as I'm calling them, also anti-commute between each other, and in that sense they appear to be fermionic. So these operators, gamma A and gamma B, even on different sites, x and y, of course, satisfy the fermionic anti-commutation relation that I've written down here. And again, that's rather easy to prove just by substituting in the definitions here. So I would have an overall factor of 1 upon I, and then I can express this in terms of commutators of the original operators. In this way. And of course we know the commutators of the original operators because they're bona fide fermions that we started with. And although some of these are 0, this is 0, for example, and this is 0, for example, these two are, of course, not 0, but rather equal to delta xy. It depends, if we're talking about the same site, x equals y, then they are, of course, finite. However, because we get one of each with a relative minus sign coming in into this expression, this is always guaranteed to be equal to 0, and so indeed these have the fermionic anti-commutation relation. So the reason why these are called Majorana fermions is because they have both the Majorana property and they also satisfy this fermionic anti-commutation relation. However, they're not really quite fermions. They satisfy this anti-commutation relation, but as we've just seen, because the particles are their own antiparticles, there's no distinction between gamma and gamma dagger. And therefore, if we look at, for example, this anti-commutation relation, gamma A x with gamma A y, this can be written out in terms of the usual anti-commutation relations of the original fermions in the same kind of way. Let's just write that out quickly. And then I get twice of the commutator Cx with Cy dagger. Again, this is 0. This is 0. This one is delta xy, and so the whole thing is actually twice delta xy. And that's because there's no distinction with the gamma operators between the dagger and the not dagger. There's no sort of concept of charge, if you like, for a Majorana fermion, because it both creates and destroys a particle. And of course, this is not what you normally get for fermions. If you take the anti-commutator of a fermionic operator with itself, then you would get 0, whereas here you get 2. So this is an unusual property that is not characteristic of fermions. And likewise, it's fairly easy to show that gamma b of x with gamma b of y, the anti-commutator of that, in a completely analogous way is again equal to 2 delta xy. So these two properties are not really fermionic-like, And that's why we call them Majorana fermions, to make sure that we understand there's a distinction from the regular kind of fermions. And these Majorana fermions have unusual exchange statistics. It's not just plus or minus 1 on exchange of the particles. So how can we understand what these Majorana fermions are? Well, it's kind of like they're half a fermion. From these definitions, you can see that gamma A is like the real part of a regular fermion. So if we take a complex number, let's say, and then we add to it its complex conjugate, then we get twice the real part. And that's because on complex conjugate, the imaginary part turns into minus itself and then it cancels. So this object here is kind of like the real part, or twice the real part, of a regular fermion. And likewise, if you take a complex number and subtract from it its complex conjugate, and then divide by I, you get the imaginary part. So these Majorana fermions, in some mathematical sense, could be thought of as the real and imaginary parts of regular fermions. So that's a rather weird property. These are completely mathematically well defined. I can always write any Hamiltonian in this representation. It's just a basis transformation. These are orthogonal, they have certain properties, which I've elucidated here. I can always substitute in these expressions to any fermionic Hamiltonian and write them in terms of Majoranas. Who cares? The interesting thing is, with the Kitaev chain, that when you do this, you learn something rather interesting. One can easily see in that case that the fundamental excitations, the basic quasiparticles of the system, are actually Majorana-like. And that's what I want to do in this lecture, but let me first just summarize these Majorana fermionic properties. So these are the important properties that we have just derived and that we want to consider. And here I have just encapsulated all of those Majorana fermionic anti-commutation relations into one single expression. Actually, another thing that we'll need if we're going to substitute these expressions for Majorana fermions into our Kitaev chain Hamiltonian is the inverse expressions. This is trivial to work out. Let me just write them down. I can write down that Cx can be expressed in terms of Majorana fermions as gamma A on site x plus I gamma B on site x, and likewise Cx dagger, the creation operator on site x, could be written as gamma A on site x minus I gamma B on site x. And again, here it makes clear that these Majoranas are kind of like the real and imaginary parts of regular fermions. So here I have gamma A plus I gamma B. If you imagine this is the real part and this is the imaginary part, that would very nicely make up a complex fermion. And likewise for this orthogonal combination here, which is just the complex transpose. So what I want to do now is simply substitute in these expressions into this Hamiltonian, the Kitaev chain Hamiltonian, tidy it up a bit, and let's see what we get. So here is the Hamiltonian and the substitutions that I want to make. Let's just do the substitution and see what we get. This is the result. We have three sets of terms, one involving the chemical potential mu, coming from the first term, one involving the tunneling between nearest neighbour sites parametrized by T, that's this term, corresponding to this term in the original Hamiltonian, and then the superconducting pairing terms, which are these final terms. And again, we're summing over the different sites in the system, x. Now, we can use the Majorana properties to tidy this up very considerably. For example, in this first term, we have gamma A times gamma A on the same site, x, and we know that's equal to 1. Likewise, gamma B on site x is equal to 1. These cross terms, however, don't vanish because of the relative minus sign between those two terms. Let's look at the second term involving the tunneling T. Here we have gamma AX plus 1 from the first term, but from the second term, gamma AX plus 1, gamma AX. And that's, of course, the commutator for the A Majoranas on different sites, which is 0. Likewise, for the B's, and likewise in the second terms. So actually, the only terms that survive in all of this are actually the cross terms involving B and A. So the final result is this. And here I've neglected the constants coming from the chemical potential term, because that makes no difference to the dynamics. And what we see is that there's a bunch of these cross terms. There's one which involves a coupling, if you like, between the A and B Majoranas within the same site. We also have a coupling between the A and B Majoranas on different sites, but you see that this is an A in site X and a B in site X plus 1, whereas this is a B in X and an A in X plus 1, and they come with different coupling strengths because we have both the T and the delta terms coming in here. So let's draw a little picture illustrating these various couplings. So this is the situation in the original fermionic bases. We have a 1D tight binding chain, where these bonds are supposed to indicate both the hopping T and also the superconducting pairing delta, and there's also a chemical potential on each of the sites. We start at the end of the chain, x equals 1, and these numbers label the site index. Let's see what it looks like now in cartoon form in the Majorana basis. So we break each site down into A and B, gamma A and gamma B, and these green circles here are supposed to indicate the sort of collection of an A and a B together forming one fermionic site. So this thing together is site 1, this thing together is site 2, site 3, site 4, site 5, and so on. So let's now draw on the interactions on this Majorana basis. So first of all, we have an internal coupling between the A and the B Majoranas on a given site, X. Let's draw that in black. That's these bonds here, within the sort of site, if you like, connecting A and B Majoranas. Then we also have two different types of term involving T and delta. We have a term that connects the A in site X to the B in site X plus 1. Let me draw that one in red. So this kind of bond looks like this. And so on. And then, oh, and I should mention, of course, that that bond strength is T minus delta. And finally, we have the last term in Hamiltonian with an amplitude T plus delta, which connects the B Majorana in site X to the A Majorana in site X plus 1. Let's draw that in blue. That clearly looks like this kind of term. So we have a kind of chain, but things have got a little bit scrambled up. In particular, these red bonds here. But we basically have a 1D chain, but of the Majoranas now, rather than of the fermionic sites. In particular, let's consider a very special limit. Let's consider the case when the chemical potential mu is equal to 0. That means that these black bonds disappear. Furthermore, let's consider the case when the tunneling T is of the same strength as the superconducting pairing delta, such that T minus delta is also 0, but T plus delta remains finite. That kills these red bonds, and what that leaves is a completely dimerized chain where the Majoranas are only coupled by these blue bonds. In particular, we see that there's an A and a B Majorana, there's an A and a B Majorana coupled, an A and a B, and so on. So what we have is a chain with pairs of Majoranas coupled, and we can think of these pairs, A and B, together, one of each flavour, making a real fermion. But something weird happened. Originally, the fermions were collected with A and B on the same site, as you see with these green kind of bubbles here, whereas in this special limit that I've mentioned, when the black and the red bonds are 0, we see that the fermionic states in the system, which mean a pair of A and B together, are actually on neighbouring sites. So it's like going from one dimerization limit to the other, and hence it has some similarity to the SSH model that we considered at the beginning of the lecture. And as with the SSH model, something weird happens at the boundary. In the original dimerization, illustrated by the green bubbles, we have a situation where all of the fermions are locked up into their respective dimers, and they correspond to the physical sites 1, 2, 3, 4, and so on. But in the special limit, when the black and red bonds disappear, we have an alternative dimerization, and the alternative dimerization looks like this. Again, this is in the special limit, mu equals 0, t equals delta. So we see that we can again collect up the A and the B Majoranas into single fermions. That's what's illustrated by these green bubbles, which have now been shifted. But we see something really weird, which is that there's one Majorana at one end of the chain and another unpaired Majorana at the other end of the chain. Of course, the actual constituents in the system are physical electrons, and what we find is that if we want to write this in terms of electronic states in this limit, we actually have a non-local fermionic state. It's an A and a B together, but they live at opposite ends of the chain. So I can sort of illustrate this by this black bubble that sort of encompasses both an A and a B. This is a genuine fermionic state because we have a Majorana of both flavors, but it's non-local. And indeed, the chain can be arbitrarily long. It can be macroscopically long, meaning that we have a single fermionic state macroscopically separated in physical real space. It is exactly localized at the ends of the chain because in their special limit, this A and B Majorana are totally decoupled from the rest of the system. They don't actually even appear in the Hamiltonian. The rest of the chain produces, as usual, a dimerized limit which is a gapped system. So we have a situation where we have a fermionic state that's non-local, which is completely decoupled from the rest. We have a zero energy state because it doesn't feature in the Hamiltonian. So this fermionic state that corresponds to these Majoranas at the end is a zero energy state. We call it a Majorana zero mode for that reason. And one of the interesting things about it, of course, is that because it's non-local in character, I cannot decohere the quantum information of this qubit, if you like, using local perturbations. I would have to do something simultaneously to both ends of the chain in a quantum coherent way in order to perturb this zero energy state. So this is really robust against decoherence from local perturbations, which are the only perturbations that really matter. So if we think about this fermionic state as like a qubit, either the state is occupied or unoccupied, then this quantum bit, if you like, this qubit, this information is stored non-locally and is robust to decoherence. So this is one of the motivations for why people might want to study such things in the context of quantum computation and quantum information. Is it possible to exploit these topological ideas for topological quantum computation? So let me just summarize. In the special limit mu equals 0 and t equals delta, the Hamiltonian takes this very simple form, which looks like a dimerized chain, but we pair up the physical fermions between the sites rather than on the sites, and in particular, we see that the gamma A1 and the gamma Bn do not feature in this Hamiltonian. What that means is that we can define a fermionic quantum operator, let's call it C0 dagger, which is 1/2 of gamma A1 minus I gamma Bn, where n is the last site in the chain. And this is this qubit state. It can either be occupied or unoccupied, but the information, as you can see, is stored non-locally. And if we consider the number operator, which is just C0 dagger C0, this tells you whether or not this site is occupied or not. And the important point is that this is conserved in this system. So the number operator for this 0 site commutes with the Hamiltonian, meaning that it is a conserved quantity. The occupation number doesn't change with time. So indeed, if we imagine a qubit, a piece of quantum information, either 0 or 1, encoded in the occupation of this site, that is completely conserved. And also, it is stored non-locally. So if I come into my system with some perturbation which acts at the end of the chain, I can't destroy this information. I would have to act at both ends of the chain, which could be macroscopically long, and indeed, I would have to act at both ends of the chain in a quantum coherent way in order to destroy the quantum information. So the idea is this piece of quantum information is robust. Now, what we considered here was a very special limit, a mathematical peculiarity of the model at a special point, but of course the magic of these topological systems is precisely that as I move away from this special limit, these states remain localized, not perfectly localized, as in this case, where they don't even feature in the Hamiltonian, but they remain exponentially well localized, in complete analogy to the situation in the SSH model that we considered earlier. In fact, you can do a transfer matrix type approach to this system equally well, and you can see that the Majorana states, are exponentially well localized at the edge of the chain. And of course, this is what we saw directly in our numerical implementation when we diagonalized the open boundary condition finite Kitaev chain, and we saw that there were exponentially low energy states, so very, very close to 0 energy states, and those states were exponentially localized at the edge of the chain. And now we understand what these states are. We understand that these are actually Majorana states, and only when you take the two Majorana states living at opposite ends of the chain can you reconstruct an entire fermion. And in case you think all of this sounds rather fantastical and pie in the sky, actually there was an experimental realization of precisely this system, a quantum wire sitting on a superconductor. And the Majorana 0 modes were purportedly observed in conductance measurements, and they were observed locally at the ends of the chain, as expected. And this is the pioneering work of Morik et al., published in Science fairly recently, only in 2012. So this is real stuff. It can be really observed. And although this is a toy model, without many of the complexities of real systems, this really captures the heart of the idea of fractionalization of electrons into these effective quasiparticles, in this case Majorana fermions, and this idea of topological protection of quantum information. So that's the end of this lecture. This is a vast topic. I'm only intending here to touch on a few interesting ideas. There are many more things that we could talk about, in particular topological insulators and Dirac semimetals and all of this good stuff. If you're interested, I suggest you read more into that. There's a vast body of literature on this.